Well, welcome to this third lecture on thermodynamics, and in this lecture I wanted to build on what we were talking on the last time, where we introduced the first law of thermodynamics and talked about work and heat and how we could calculate changes in internal energy. So we did a lot of work about calculating work and talked a little bit about determining heat of reactions, but finished up with this idea that we can, instead of thinking about changes in internal energy, we can instead think about changes in enthalpy, where enthalpy is the sum of the internal energy plus the pressure volume work. So this means we don't have to constantly think about the heat loss and the work loss or gain in a chemical reaction. So that means now we change our y-axis for the purpose of this conversation to enthalpy, H, and therefore a change in enthalpy between reactants and products is going to be positive or negative. And as I'm sure you all know, if our change is positive, well, that means the products minus the reactants is a positive value. So that means our products are higher in energy than our reactants. So therefore this is an endothermic reaction. We have to give an amount of enthalpy to this reaction, indicated by this gap here. So we have to supply the system with this amount of enthalpy, so therefore it's an endothermic reaction. More commonly we tend to have exothermic reactions, so this is where the energy of the products is lower than the energy of the reactants, so therefore the system has given off enthalpy and so it has lost that amount of enthalpy, so the change is negative. So for endothermic reactions, enthalpy change is positive. For exothermic, enthalpy change is negative. So one thing we want to just recap is the issue of thermodynamic notation. So let's say we're talking about enthalpy. Very often we will have changes in thermodynamics, so we use the delta symbol, capital D, to indicate that we are talking about a change in the substance. So here we have delta H, meaning a change in enthalpy. We can then say what kind of reaction it is. So very often we will use a notation indicator to indicate what type of reaction it is. So here I'll put in a subscript C indicating it's a combustion reaction. We can also use OR just for general chemical reaction, or as we will see throughout the course, there are different subscripts here that indicate particular types of chemical reactions that we use. Most often we report values, standard values, using this Plimsoll sign, this sort of circle with a line going through it. And this indicates that the reaction conditions were what we call standard conditions, and I'll mention those in a moment. And that means then if I talk about my value that I've calculated at standard conditions, somebody else can compare it with their value. Standard conditions don't include temperature, so if we do measure a change in a quantity at a particular temperature, we can note the temperature that we've measured the change at. So this thermodynamic notation essentially allows us to write out a change or a description of change using very sort of concise notation. So we have our delta symbol indicating change, or indicating the type of process being considered, the thermodynamic quantity itself we're talking about, the Plimsoll indicating we're under standard conditions, and here on the right you'll see what the standard conditions are. They don't include temperature, so therefore we include the temperature of reaction. So you should just get used to this kind of thermodynamic notation. You may often see in textbooks that the OR here indicating the chemical reaction type comes after the thermodynamic state function. We tend to put it before more often now because that will obviously get in the way of the temperature that we're reporting the value at. One thing that we need to know early on is when we talk about enthalpy changes, we need to start coming up with some standard value, because we need to be able to afford substances as standard enthalpies. And we use the enthalpy of formation as a way into this. So the enthalpy of formation is essentially how much enthalpy is lost or gained in the formation of a substance from its elements in their standard states. So if we combine elements to form a molecule and they require heat to form, well then that's an endothermic enthalpy of formation. If substances, so for example sodium chloride, when sodium and chlorine react, they will give off a lot of energy, a lot of enthalpy, so that has an exothermic enthalpy of formation. So enthalpies of formation is an important value because it tells us how much energy a substance requires or gave off in its formation. Because we're using elements as a way to explore this or to elicit this, by definition the enthalpy of formation of any element is zero. If elements already exist, it doesn't take any enthalpy to form them. And what we call the NIST book has lots and lots of data that you can easily gather for lots and lots of molecules. Why is this important? This is important because we can use enthalpies of formation in working out enthalpies of chemical reactions. So here we have our chemical reaction. This is a combustion reaction, so we use the C notation here indicating this is enthalpy of combustion. And again, this is giving us our chemical reaction. Here this is a combustion reaction of organic substance with oxygen to form carbon dioxide and water. That's a combustion reaction. And we can use enthalpies of formation to work out the overall enthalpy of this reaction. How? Well, if we look at our reactants going to products, well, each of these reactants will have their own enthalpy of formation. So this is like a sort of a measure of the enthalpy of that substance. Each of the products will have their own enthalpies of formation. So therefore the difference between reactants and products will be the differences between the sums of those enthalpies of formation. So here I can write this as we've got our reactants going to products, and we know that the enthalpy of reaction will be the difference in enthalpy between reactants and products. So this delta H value, this change between reactants and products that we're interested in thermodynamics, is the difference between those two. So if we use our y-axis as enthalpy, well then that means then if we can afford some energy values or enthalpy values to our reactants and to our products, well then obviously the difference between those will be the enthalpy of reaction. And what I'm saying is that we can use enthalpies of formation as those values. So we can say that the enthalpy of formation of sucrose is minus 226.1. In other words, when sucrose forms from carbon, hydrogen and oxygen, it liberates that amount of energy in its formation. Oxygen is an element, so therefore it has an enthalpy formation of 0. And similarly for carbon dioxide and water, once we know their enthalpies of formation, we can add them up. 12 times the value for carbon dioxide, 11 times the value for water, and that we can add that up to get minus 7865. That means the enthalpy of this reaction, which is a combustion reaction, will be the product's value minus the reactant's value, minus 7865.8 minus 226.1. So we get a value of minus 5639. So this use of enthalpies of formation is a really powerful way of working out enthalpies of reaction, because it means we don't have to go into the lab to actually work it out. We can just use enthalpies of formation to work that out. So here we had our sum of enthalpies of formation of our reactants, sum of enthalpies of formation of our products. So that means we can work out the enthalpy of reaction, products minus reactants, by saying the sum of the values of products minus the sum of the values of reactants gives us this enthalpy of reaction. Okay, so this is a really useful way of working out enthalpies of reaction, because, as I say, there are textbooks effectively of values that we can look up, these standard enthalpies of formation, so we can work out what the enthalpy of reaction is without having to go into the lab. So let's have a look at another example. So here we can see we've got our reactants and products, and we're told the enthalpies of formation of our reactants and of our products. So our reactants here are iron oxide and ammonia, forming FeO, water and nitrogen. Alright, so our enthalpy of reaction is the sum of the enthalpies of formation of products. So it's our FeO value. So FeO value is minus 226.3. There are 6 of them. Our water value, 3 times the value for water. And our nitrogen value. Well, we're not given nitrogen, but nitrogen is an element, so therefore it has an enthalpy of formation of 0. So there are products, and we can subtract from that our reactants. And our reactants are 3 times the value for iron oxide, so minus 824.2 times 3, plus 2 times the value for ammonia. So we just need to be careful when we're working through this that we're careful with minus by minus multiplications. So when we work that out, we get a value of products minus reactants, which is 109.6 kilojoules per mole. Alright, so slightly neater. I've got my product values minus my reactant values, and I get an enthalpy of reaction. We can see here that we can determine whether or not enthalpies are endothermic or exothermic by exploring which particular scenario it is. So you might have a look and see, well, which scenario is represented here? Is it A, B, C, or D? And what we can say is that we know that the enthalpy of reaction is positive. So that immediately excludes A and B, because in both of those cases these are exothermic reactions. The enthalpy here, the energy of products, is lower than the energy of reactants, so it's neither A nor B. So we're left with C and D, but you see here in C the barrier notation is not the difference between energy of reactants and products, it's actually the barrier of the reverse reaction to overcome that hump. So therefore the answer is D. The difference in energy between reactants and products is this positive value, delta H, 109.6 kilojoules. We can do this kind of thing because enthalpy is what's called a state function. And a state function is essentially a function that doesn't depend on the path of change. So if we think about altitude, for example, if I was to go straight up a funicular, straight up the side of this mountain from bottom to top, or if I was to walk the path wrapping around this mountain from bottom to top, the difference in height between bottom and top is the same. It doesn't matter which way I take, the difference is the same. And this is a state function. State functions mean that we don't have to worry about the path of progress. The overall difference will be the same. And in chemistry, and those of you studying physics really need to note this because it's different in physics. They use different notations. In chemistry, we always use capital letters for state functions. So for example, H is a state function. U, internal energy, is a state function. But you might have noticed that Q, heat, or W, work, are not state functions. They depend on the path taken. So this means then we can use what's called Hess's Law, which is effectively, we've been applying this in a special circumstance of enthalpies of formation, but Hess's Law says that the enthalpy change for a reaction carried out in a series of steps is equal to the sum of the enthalpy change for the individual steps. So in other words, if I have to go from one place to another, it doesn't matter how I get there, the distance as the crow flies from that first place to the second is the same. Okay, and we can use Hess's Law by way of, we can use information in Hess's Law to essentially do jigsaw puzzles to work out enthalpies of reaction. So here we have a reaction at the fermentation of sugar to form alcohol. So this is happening when we ferment alcohol. And this will produce 2 moles of ethanol and 2 moles of carbon dioxide. And here we have a reaction where we don't know the enthalpy. We don't know the enthalpy of this reaction, but we are given 2 pieces of information. And those 2 pieces of information are that the enthalpies of combustion of glucose and ethanol are these values. So we can write out those equations. Enthalpy of combustion of glucose and ethanol are given by these 2 equations here, 1 and 2. So the task now is to look at what we call our target equation. So our target equation is this one in blue at the top, this equation where we don't know the enthalpy. And we essentially then look at each of our given equations and see how they match up with the target equation. So what we can say is when we look at equation 1, for example, we see we have 1 mole of C6H12O6 on the reactant side. In our target equation, we have 1 mole on the reactant side. So we leave equation 1 as it is. Equation 1 just is essentially the same equation, C6H12O6, combusting with oxygen to form carbon dioxide and water. We don't do anything with that. Why? Because we have 1 mole of our desired reagent on the left hand side in that equation. So therefore the delta H for that doesn't change. When we look at the second equation, we see we have ethanol on the reactant side. In our target equation we have 2 moles of ethanol on the product side. So therefore we need to reverse equation 2 and multiply it by 2 to give us our desired equation. So if we reverse equation 2 and multiply it by 2, that means we've got 4 moles of carbon dioxide, 6 moles of water, forming energetically, okay, this is a paper exercise, forming 2 moles of ethanol and 6 moles of oxygen. We're reversing this equation and multiplying it by 2, so therefore the enthalpy of that is plus, because we're reversing the equation, and we multiply 1368 by 2 to give us 2736 kilojoules. So now what I have to do is just sum these up. So if I sum these up, I can cancel out some of the reagents on both sides. So we see that, for example, we have 6 waters on our reactant side, they cancel with 6 waters on the product side, there's no reaction there. 4 of the carbon dioxides on the reactant side are cancelled out, so we're left with 2 carbon dioxide on the product side. 6 oxygens cancel out with 6 oxygens, so I'm left with C6H12O6 as a solid, forming a CO2 plus 2 CO2 plus 2 moles of ethanol. And now to get the enthalpy of this reaction, which is the enthalpy of reaction for our target equation, all I have to do is add up those enthalpies, Hess's Law. I just have to add up those enthalpies of the individual steps to get the overall enthalpy change. So that leaves me with 72 kilojoules per mole. Okay, so we just essentially rearrange these given pieces of information, 2 pieces of information, rearrange those to find out the enthalpy of reaction for our unknown. Okay, so far we've been talking about 298 Kelvin, everything happening at standard temperature, standard conditions, and 298 Kelvin. But what happens when we change the temperature? So when we change the temperature of a substance, how is that going to change its enthalpy? And what we find is that in our chemical reaction here, for example, we are going from reactants to products, and that will be at a particular temperature. So let's say that's a temperature T1. So here, in this case, this is an exothermic reaction, but here, for example, the difference there, that enthalpy will be a given value at that temperature. And the reason we quote it at a temperature is that the enthalpies of substances will change as the temperature changes. Why? Because we are changing the motion, vibration, rotation, and so on of the substances. So therefore the ability of heat to flow through those substances, okay, remember our calorimetry formula, Q is equal to MC, heat capacity, delta T. So therefore the ability of heat to flow through those substances changes. So its enthalpy will change. The ability of it to pass out or take in heat will change. So that means that if we carry out the exact same reaction at a different temperature, it may have a different enthalpy, because the enthalpies of reactants and the enthalpies of products will have changed, and they may not have changed by the same amount. In other words, these are not 2 parallel lines. So that means now we need a way of thinking about enthalpy change as a function of temperature. And the way we do this is to go back to our calorimetry formula. So the calorimetry formula says Q is equal to delta H, a constant pressure, is equal to the heat capacity, a constant pressure. Okay, so this Cp here, this P is just because we have to keep it a constant pressure to relate Q and delta H, times delta T. All right, this is for this is the molar heat capacity rather than the specific heat capacity. So if we change this, reduce this to infinitesimal amounts, that means instead of writing delta H is equal to C delta T, instead we say dH, the derivative, dH is equal to C dt. And because we can assume, or because we will assume, the heat capacity is constant across temperatures, not a great assumption, but nevertheless we will assume that, we can then integrate. So here we've got the integral from one enthalpy to another. In other words, we're interested in how, if I go back to the previous slide, we're interested in how enthalpy is changing across temperature. So we're just looking at some infinitesimal increase here. So we can say the integral from one enthalpy to another, dH, is equal to Cp, a constant taken outside the integral, from one temperature to another dt. So that will give us H2 minus the H at temperature 2 minus the H at temperature 1 is equal to C upon temperature T2 minus temperature T1. So we can easily then reduce this expression down to what is known as Kirchhoff's law. That says that because this applies for enthalpy, it will also apply for change in enthalpy. Kirchhoff's law says the enthalpy at a given temperature will change by this amount delta Cp delta T to give us the enthalpy at a new temperature. So we are able to work out by how much will this increase or decrease depending on how much we change the temperature, and that is all dependent on the change in heat capacities. How much do the heat capacities change in this substance when we go from one temperature to another? Okay, and remember this is all about the molecule and its ability, the ability of heat to pass through that molecule. So this change in heat capacity, as you can guess, is the change in heat capacities of the products minus the change in heat capacities of the reactants. So that means then we may work out the enthalpy of reaction at 298 Kelvin, but we might need to do this process on an industrial scale, and we might need to really ramp up the temperature. We could figure out then what will the enthalpy change at the much higher temperature be by using Kirchhoff's law. So we need to do this, we need to work out, we need to be told what the molar heat capacities are. So you know if you see a question where you're given the molar heat capacities that you're going to use Kirchhoff's law. Alright, so here we have the standard enthalpy of formation of a substance is this. So this is our delta H at T1, 298 Kelvin. And you want to know what is its value at a different temperature, 100 degrees Celsius or 373 Kelvin, based on these molar heat capacities. So this is pretty straightforward. We can use Kirchhoff's law. Delta H at the second temperature, 373, will be equal to delta H at the first temperature, 298, so we know that value, plus the difference in heat capacities upon the difference in temperature. Alright, and here you just need to be careful because of course heat capacities are in joules per Kelvin per mole, and the enthalpy is in kilojoules per mole. So you just need to make sure that we keep the units consistent. So this will be minus 241.82 by 10 to the power of 3 joules per mole plus the difference in temperature times the difference in heat capacity. And what we see is a very small change, very small difference between the first temperature and the second temperature. Alright, that's the sort of first main part of enthalpy that I want to talk about. When we go on to the next section, we'll be introducing how we can actually start to use those concepts in measuring more complicated, using more complicated experimental techniques. But just to mention, if you're starting to keep track of the equations that we've been using, there's an equation sheet on Learn, so you can see these are the equations that we covered in the first lecture. In the second lecture, we talked about the ideal gas law, and then relating. We wanted to get more of a handle on Q and W, so we did a lot of expansion on Q and W. And then after all that hard work, we introduced enthalpy, so we wouldn't have to worry about pressure volume work. And this lecture now has been about enthalpy and starting to play around with enthalpy. So we'll pick that up in the next section. There are some questions on Learn, and you should have a go at these. These are past exam questions. I've just scrubbed out the bit of the question here that we haven't got to yet, but we'll be able to pick that up later in the course.